Okay, so welcome to this video recording. This is actually the second part on topic 7.3, the exponential function. It is a continuation of the lecture that I have not managed to complete this morning. In this second part of the lecture, we are going to discuss the differentiation and integration that involve an exponential function and the generalizations of this. So let us look at the questions of the derivative of the exponential function. So the question is very simple. I have a function of e power x, and I want to know what is the derivative of it. To answer this question, you have to make use of two knowledge. First is the knowledge of the what you call the logarithmic functions. So the logarithmic function is the inverse of the exponential function, and the exponential function is obtained from the log by inversing it. That is, you reflect the natural log onto the y equals to x-axis, then you get this graph which represents the exponential function y equals to exponential of x. So the exponential of ex is expressed and calculated as the exponential of x. Okay, so we have explained this in the first part of the lecture very thoroughly already. So now I ask these questions. What is the derivative on a point that is sitting on the exponential curve? So let's say this is a point of, say, A and B. So I want to know what is the derivative at this point. So specifically, I'm asking the questions, what is the derivative of the exponential function at the point where x is equals to A, where A is the locations of the x value. Okay, so at any arbitrary x, then what is the slope of the exponential function? So the derivative of the exponential function at the point x equals to A is related to the derivative on the corresponding point sitting on the natural log function. So if this is the original point sitting on the exponential function, the corresponding point which is obtained by reflecting AB along the y equals to x-axis is the point of B of A, where this point with coordinate x equals to B, y coordinate equals to A is sitting on the logarithmic function. So the derivative at this point on Ex is closely related to the derivative on this point sitting on the logarithmic function. And we have already studied and discussed the relationship between these 2 points. Okay, specifically the derivative of the exponential function at this point is equals to the reciprocal of the derivative at this point. This is a point sitting on the logarithmic function which has an x coordinate equals to b. So the derivative at this point on the logarithmic function here is this. It is the derivative of the natural log at the point where x is equals to this number, which is b. Okay, so this is the relationship that relates the slope or the derivative on the exponential function and the derivative on the logarithmic function. So you have to be careful at which point the derivative is calculated. This calculates on the exponential function, the derivative is calculated at the point A. The derivative on the log function is calculated at the point x equals to b. So that is the general relationships that relates them. So now we have to be a little bit careful to relate x and b together. So here this a and b are actually closely related. So maybe I should just look at this point here. So if b is sitting on the exponential curve, it means that this is the value of x. Then when x is placed in the exponential function, then you got a b. Therefore, the relationship between a and b on this curve is that b is equals to e power a. Okay, so that is the relationship between a and b based on this point. If you look at this point, b is the values that goes into x, and the result of ln at b is equals to a. So based on this point sitting on the logarithmic function, then you can write down the relationship between a and b as a equals to ln b. Okay, so here on this point, b is e power a. On this point, a is equals to ln b. So we have a very nice relationship between b in terms of a or a in terms of b. So now we can continue to derive the derivative of the exponential function at the point a. So we are going to look at this one, and we'll try to express whatever that is on the right hand side of this equation in terms of a. So let's see how we do it. So it's very simple. d dx of ln x is known because d dx of ln x is just by definitions 1 over x. So this is 1 over x. So 1 over x is just equals to x. So therefore, this term is equals to x. Maybe I should write it like this. That is equals to x evaluated at x equals to b, which is just equals to b. When you substitute x by b, and b is related to a through this relationship here, right? So b is nothing but then you express it as the exponents of a. Okay, so what I have done here, I have shown that the d dx of exponents of x evaluated at the point a is the same as the exponent at point a. Right, this left hand side is coming from here, then right hand side is coming from this term. So it says here the derivative of ex is the same as the exponential value at the same point with the coordinate of a. So this is equivalent to the statement that d dx of e power x is equals to e power x, because on this side this a, this is side of a. So if you like to, you can replace the a by any arbitrary x. Okay, so that is the result of the differentiation of the exponential function, which is equals to the exponential function itself. So that is a very simple relationship. So the next thing we want to do is to generalize this relationship to a case where x is to be replaced by the general function of x, right? So this is what we call a generalization. Instead of just e power x, we generalize x to any arbitrary function. So we want to ask the question, what is the dx of e raised to any power of u, where u is understood to be a function of x, say for example x squared, sine x, or cos x. So this could be easily obtained by using the chain rule, that is d dx of e power u is just equals to du dx and then e power u. Okay, so that is the chain rule, where this term is coming from the fact that this is d du of e power u, which is e power u. So the generalizations of this differential rule for the exponential function is d dx of e power u equals to e power u du dx. This is obtained simply by applying the chain rule to this equation. Now, once we have obtained the generalized differentiations of exponential function of e power u, then we proceed to obtain the integration version of this equation, right? So I have mentioned this earlier on in other parts. That is, if you have a function or capital F and you differentiate it with respect to x and you end up a new function of f, that means the capital function f is the antiderivative to the small function f. So you make the statements that capital function f is the antiderivative to f by saying that the antiderivative of the small function f is represented by this indefinite integral, right? This indefinite integral says it represents the antiderivative of the small function f, and the antiderivative is f, and f is just one antiderivative. So if add the antiderivative to any arbitrary constant, it will still be an antiderivative to the small function f. Therefore, this transfer to this equation. So here you compare this with these situations. So it is understood that the f here, capital F here, is the e power u here, and the f here is e power u du dx. Therefore, you write down this version of equation for here, that is d dx of e power u equals to e power u du dx. When you write it in this indefinite integral form, it will be like this. Okay, with the indefinite integral of the small function f. What is the small function f here? It is this one, which is the right hand side of this equation, which is e power u du dx. And then don't forget you have an dx term. Then you have on the right hand side the antiderivative capital F function, where this capital F function is played by the rule of by the expression of e power u. So you have e power u plus n constant. Okay, so here you look at this one again, du dx times dx by definition is just the differential of u. We have learned this also many times. Therefore, I replace this expression by du. So e power u integrate with respect to the variable u is equals to e power u plus an arbitrary constant. So this is the integration that involve the exponents of e power u, right? So we have up to this point derived the derivative of e power x and its generalization. Then from this generalization differential rule, we derive the integrations that involve e power u. So now we are going to show some simple example that involve the differentiation and integration of a function. For example, the differentiation of this one is simply equals to 5 times d dx of e power x, and d dx of power x is just e power x. So there's nothing special about this one. Okay, so so these 3 slides is just the derivation of this relationship, which I already demonstrated. So now let us try to look at equations, example 7a, e power 3x, integrating from 0 to ln 2. So let me try to translate these questions into my whiteboard. So it is e power x, e power 3x dx, and it is to be integrated from 0 to ln2. ln2 is a number. So this could be easily understood and integrated by using a suitable substitution. So the tricks on example 7a and b, both cases, now we're doing a, but we're going to do b, is to try to cast the integration into the form of e power u eu. Once you are able to cast the integrand into the form of e power u, integrate with respect to u, then the solution will be just simply equals to e power u plus n constant. Okay, so try to do this on the 7a example. We are trying to do this, but this is not u because this is 3x, this is only x. So is a very straightforward substitution to do. You just replace 3x by u, then du is equals to 3 dx. So you can now translate the integration with respect to with respect to x into the integration with respect to u. Now I would like to introduce the values of u2. u2 is equals to, say, this is x2 and this is x1. So I define x1 is the lower limit in the integration, and x2 is the upper limit in the integration with respect to x. So u2 is the function of 3x evaluated at x1, which is equals to 0. And u1 is a value of the function evaluated at x2, which is u of ln2, which means is ln2 multiplied with 3, right? So because u is 3x, so u at ln2 is just 3 times ln2. I think I have done some minor mistakes here. So here this should be u1, this should be u2. Okay, so now I am ready to translate the integrations from the variable x into the integration with respect to the variable u. So dx, according to the substitution rule, du is just 3 dx. Therefore, dx is just 1/3 of du. So I have 1/3 of du, and e power 3x is e power u. So now I have successfully translated the integration of e power 3x dx into just this form of e power u du. But I have to also translate the limit of x into y. Therefore, here x1 become u1, x2 become u2 in the integration with respect to u. So now this is equal to 1/3 of e power u2 minus e power u2 minus e power u1. So it's correct. So then I just substitute in the values of e power 3 ln2, right? 3 ln2 is ln2 raised to power 3, using the rule that ln x power r is equals to r ln x. Okay, I think this is n. Never mind. Therefore, 3 ln2 is ln2 power 3, which is ln 8. 2 power 3 is 8. Therefore, I have the values of u2 here is ln 8 minus e power u1. u1 is 0. And e power 0 is just equals to what? Is equals to 1. Okay. Now, how do you know e power 0 is 1? You can understand e power 0 equals to 1 again from the constructions of the exponential function from the logarithmic function. Okay, for the logarithmic function, when x equals to e, the values of this point is e at 1 by definition. So if you translate this point into the exponential function curve, then this is a point of e power 1. Then this point is translated into this point here. Sorry, I think I have drawn the wrong point. I'm sorry about that. So I have to draw this again. The values of e power 0 could be understood from not on the point of x equals to e, but on the point of here. So when x equals to 1, the values on this point is equals to 0. So when you translate this point onto the exponential function, this point 1, 0 is translated into 1, 0. So this is a point of 1, 0. It means that when x equals to 1, exponential function at 1 is equals to 0. Right? So based on this point here, with the coordinate of 1, 0, it simply means that the exponential function evaluated at 1 is 1001. Sorry, this is again, I made some stupid mistakes. I try to go too fast. No, that's always happen. So 1, 0 translated into this point become 0, 1. Okay, so this says when x equals to 0, the y equals to exponents of 1. So this says e power 0 should give you 1. Right? So this could be easily understood as from the viewpoint of the values of the exponential function on the curve that is obtained by reflecting log of x. So e power 0 is just 1. Then we can then simplify this to be e power ln x, ln 8 is just equal to 8 minus 1, which is equal to 7 over 3. So that is the integrations that I am doing. So I'm integrating log exponential 3 and 2 and 0. So let us try to verify this using Mathematica. This is always possible. So let me integrate the exponential function of 3x, and then you let x to start from x1 to x1 to x2, where my x1 is just values of 0, and then the x2 is the log of 2. So Mathematica log of 2 is start as log at 2, and when I press the button shift enter, I expect a number which should be equals to 7 over 3. So do I get 7 over 3? Yes, I do get 7 over 3. That means the answer for my integration is correct. So fortunately, it's correct. So now we go to 7b. We have e power sine x cos x integrating from 0 to pi over 2. So let us look at this integration. E power sine of x cos of x dx. And the range of integration is from 0 to 90 degree, which is pi over 2. So to do this integration again, we have to cast this into the form of e power u, eu, with lower limit u1 and upper limit u2. And this could be easily obtained by looking and comparing this with this one, where you see that sine x is suitably replaced by u, and if you replace u with sine x with u, then the differential of u give you cos x dx. So that is kind of straightforward. So you let u equals to sine x, then du is then equals to cos x dx, and then I'll call u1 to be the values of sine at x1, where x1 is 0. I call x2 as pi over 2. So u1 is then equal to sine of 0, which is equal to 0. u2 is defined as the function of sine evaluated at x2, which is sine of pi over 2, and which is equal to 1. So u1 is 0, u2 is 1. Therefore, I can now proceed to write down the integrations of this integrand with respect to x into the integration with respect to u. So e power sine x is just replaced by e power u. Then cos x dx, as explained here, cos x dx is just replaced by du. So I have now successfully converted the integration with respect to x into the integration with respect to the variable u, and I have u1 here and I have u2 here. So I have e power u2 minus e power u1, and I also know what is the values of u1 and u2. So u2 is 1 and e power of u1 is 0. This is e minus 1. So this is the answer. So if you use Mathematica to check, then you should get the exact answer. I've checked it and the answer is exactly the same as expected. So that's how I can perform integrations that involve e power u du. So the next thing we want to talk about is how to numerically obtain the values of the natural number e. So the trick is actually quite simple. In order to obtain the numerical values of e, what you need to do is to calculate the derivative of an function f prime at the values of 1, where the function f is defined as x of x is defined, f of y is defined as the log of y. So here I use the y as the variable, then f is just the function of ln y. So derivative of y is easily equals to 1 over y, and the derivative of y of f at y equals to 1 is then equals to 1. So the values of e can be obtained by evaluating the derivative of the log function at 1 by not using this result, but what we are going to do is to write down the derivative of the log function at the point x equals to 1 using the definition. Right, so how do you do that? It's actually quite straightforward. So you have a function of f which is equals to ln y, and this is y, and this is 1. Right, so the function is like this, and we are going to calculate the derivative of the function f prime at 1, which is the derivative at this point. So we are going to do this by using the definition of derivative. So say you have a point here, I just call this, say, h, right? So this is just at h distance, therefore this point is then h plus 1. So the derivative at this point is defined as the function of log of y evaluated at h plus 1 minus the function evaluated at 1 divided by h, and then we take the limit of h going to 0. So we are going to continue from here and work out the details of this. So here I write down the limit of h0 and the function of f of 1 plus h. So the function of f is, as I mentioned, by definition, is the log of y, right? So therefore, the f at 1 plus h is nothing but just the log at 1 plus h minus the values of the function log at 1, right? This log of 1 is just this number, and then I have the values of h downstairs. Okay, so we proceed. Copy down the limit procedure. So this is 0. Log of 1 is 0. So what happened is you have these expressions. So what is this expression? This expression is actually 1 over h of ln 1 plus h. And since we know the product of a constant times the log of say another function, say r, is the same as ln r power x. So here we can rewrite this expression as ln of 1 plus h raised to the power of 1 over h. Okay, so that is what I'm going to write for the next line. This would then be equals to ln of 1 plus h raised to the power of 1 over h. And then I'm going to take the limit of the log of this expression by shrinking h to 0. So when I shrink h to 0, what do I get? What I get is the values of the derivative of the log evaluated at 1. And what is this? This is just equals to 1. And therefore, the limit of the function should equals to 1. So let us proceed from here. Let's just look at this situation. We have a situation where you have a limit of the log of 1 plus h raised to the power 1 over h. In the limit h goes to 0, you get 1. So we have a situation like this. You have a limit of h going to 0 of the log of something, and it's going to become 1. So what can you conclude about this something here? So this something here, it must be, okay, it must be equals to e, right? Because for whatever h it is, if you have one log of something equals to 1, then inside here, it must be equals to e. It means that this thing must be equals to e when h goes to 0. So with this argument, then I write down the following statements. That is 1 plus h raised to the power of 1 over h in the limit of h goes to 0 it must be equals to e. So that is how e is expressed as the limit of 1 plus h over raised to the power of 1 over h. So I can do a better job by replacing h by a variable of x. So I just look at it, I don't like h here. I just replace h by x. I just somehow like to express the limit in terms of x. It looks more appealing to me. Okay, so this is 1 over x. So in order to get the number, try to calculate this limit. Okay, so how do you calculate this limit? I think this limit could be calculated at least numerically by using Mathematica. So let's just try to use Mathematica to do this. It should give me an correct value. So Mathematica can also take a limit. So you say limit, limit of what? 1 plus x raised to the power of 1 over x, and you let x goes to 0. So when I press the shift enter button, I should get values of e, which is the case. So that shows how to obtain the values or numerical values of e using the limit method. And then this number is obtained by using numerical method. So that is what this slide is about. So let us move on to the next slides. So the next slide is about the generalizations of the power function and the exponential function. Okay, so far we have already explained to you what is the exponential function. So exponential function is the inverse of the logarithmic function written in this form. Now, once we have established the definition of the exponential function and it is defined for all real values of x, then we can make use of this exponential function to generalize the exponential function. So in the beginning of the 110 lecture, I mean the few weeks, in the first weeks where we begin the course, we have mentioned what we call an exponential function, right? Exponential function. So when we introduce exponential function, it is say that a is any positive real number, right? Positive real number, that is a positive number, positive rational number, not real number, but positive rational number. So for any positive rational number, the values of a positive rational number raised to an rational number of x is easily understood. However, when you make either a or x as real, that includes an irrational number, then this exponential function will not be well defined. So now we would make use of the exponential function to define a general exponential function in which the exponents as well as the base could both be irrational number. Now, how to do that? This could be done by rewriting a power x into this following form. So this is equals to a power x. So I retain the x outside, and what is inside here should be a values of x. So what I'm going to do is I'm going to take the exponents and I take the log of a. Right? The exponents of log of a is giving me back a itself. It's just that I rewrite a in terms of e raised to the power of ln of a. Okay, so that is the way how I do it. Then we also understand from the previous discussion in this first part of the lecture, if you have exponents of x1 raised to the power of 2, this is the same as e power x1 power x2. Okay, so this is then equals to e power of x times ln a. So making use of this rule for the exponential raised to another power of x2, then the result is the same as e raised to the power of the product of x1 and x2. So I have this equation which represent the generalization of the exponential function, where in this case x can be also an irrational number. The reason is because e power x is defined not only for real number but also for irrational number. Right? Without this definition, then you could not raise a to an irrational number. And a here could be just any number, and it is defined for all positive number of a that is rational or irrational. So anyway, this is a generalization of the power function that allows the powers x to include irrational number. So without the exponential function, then you can't generalize to a power x for any irrational number of x. So the next thing we want to do is to make use of the exponential function to generalize the power function. So this is a generalization of the exponential function. Okay, so this is the exponential function. I write it down here. Generalize exponential function. Okay, so that is this bit. Now, once we have discussed the generalized exponential function, let us proceed to apply the definition of exponential function of x to another type of function. The other type of function sometimes get me confused. What we are talking about here is the power function. So the power function and exponential function looks very similar, but they are actually different. So for an exponential function, you have a constant raised to an variable, whereas for a power function, you have a variable x raised to an power of n. So in the beginning of our course, we also mentioned about power function. However, in this case, the powers, that is the power of n in the power function, is only limited to rational number. If this power n is not a rational function and rational number, but an irrational number, then you really can't define how to calculate it. However, with the invention of the exponential function, you can now define x raised to a power of any real number, including irrational number, as the same as what we do for the exponential function. That is, you raise this to equals to e power n ln x. So that is how you generalize the power function to include a power which is also defined for irrational number. The reason this is possible is because the exponential function is defined for all real number. So it is allowed for the n to become irrational as well, right? So e raised to the power of any irrational number could be is defined in the exponential function. If the right hand side is defined for any irrational number, so is the left hand side. It will be then defined for x power n for any irrational number. So that is how this is obtained. Now this could be easily seen to be the case if you would look at it more carefully. Now this is indeed equals to this. Now how do you see that? Let's try to see if I can see this myself. Okay, so let's try to see this x power n is equals to e power n ln x. So let me look at this expression independently. So e power n ln x is equals to e power ln x power n, right? So this is the same as x power n, right? So x power n can then also be expressed as e power ln x power n. Then this again is e power n ln x. So you can define x power n as e power n ln x. So operationally speaking, in order to calculate the values of this, what you do is first you calculate what is the product of n ln x. So x could be any positive real number, including irrational number. N could be any number, any real number, including irrational number. So the product of an irrational number and another irrational number could possibly become another irrational number. So this irrational number is defined and could be calculated for e power n ln x, right? So you can read off this number from the exponential curve. Then this number is defined. Then this number is just equals to the values of x power n for n that is possibly irrational. So up to this point, we have made use of the exponential function e power x to generalize the exponential function. We have also made use of the exponential function to generalize the power function. The next topic that we are not going to discuss live lecture, but is going to be delivered in a recorded lecture, is about the generalized exponential function. So the general exponential function has an inverse. The inverse of the generalized exponential function is called log of x base a. So the properties of the exponential function and its inverse will be discussed in, I think, chapter 8. So you look at chapter 8 for more details about the a power x and the log x of a. So up to this point, we are going to discuss a little bit of example on the generalized exponential function and the generalized power function. So this is the derivative of the generalized power function, and then this is the generalization of the exponential function, which I already discussed in detail. So the next thing you want to do is to calculate what is the derivative of the generalized power function. Okay, so we have already done this for the generalized exponential function. Sorry, the generalization of the exponential function EU. This is equal to EU. But we have not discussed the differentiation of the generalized exponential function. This is actually discussed in more detail in chapter 8. So here we are not going to discuss the differentiation of the generalized exponential function, but instead we are only going to discuss the differentiation of the generalized power function, and it turns out to be just equals to n times x power n minus 1, where n is any real number, which could be also irrational. So this formula looks very, very familiar, like what we have discussed when we discussed the differential of x power r for the power function, where the power is an rational number. So this is seen before. It appears to be exactly the same, but it is different, right? So in the previous sections, the power in R is only rational, but here the power in X, the power here n is could also be irrational. Now this formula is actually not the same as this one, in the sense that its derivations is totally different from this one. So the generalizations of the function here to this version has to be done quite independently. So we are now going to prove how to get the differentiations of the generalized power function. So this is what we are going to discuss now. d dx of x power n is equals to what? So the correct way to do this is by looking at the definitions of the generalized power function. So I mentioned the generalized power function, where n is possibly irrational and real, is defined as e power n ln x. Okay, so what you do is then you would let u to define n times ln x. So then I have this y equals to xn equals to e power u. So I want to know what is du dx. So this is the same as asking the same question, d du of x power n. So the calculation of this is to take the derivative of e power u with respect to x. So the right hand side here is a differentiation of e raised to a general power of u with respect to x. Therefore, we apply the chain rule. The chain rule says this is equals to du dx and d du of e power u, which is just e power u du dx. Okay, so here you have e power u and you have du dx. So this is just equals to du dx e power u. And what is the du dx here? Du dx could be easily seen from here. So you look at this one, then you write down the expression of du dx. Du dx is simply equals to n times d dx of ln x. Here n is a constant, therefore you can pull out the constant when you differentiate with respect to x. So that is n. D dx of ln x is equals to n of times x power minus 1. Right? This is just trivial. D dx of ln x is just 1 over x. Therefore, the right hand side here for these equations is nothing but just e power u times n x minus 1. But what is e power u? E power u is nothing but just x power n. Right? I just replace this by u. So e power u is x power n. Therefore, this is x power n multiplied with number n and x raised to power minus 1. So this is equal to x n times x of n minus 1. Therefore, the conclusion is that here d dx of the generalized power function is equals to n times n minus 1. So it looks like the previous equations for the derivative of x power and rational number, but the arrival at these equations is tremendously different from this equation, how this right-hand side equation is derived. Here, the derivation has to be depend entirely on the definition of the exponential function, whereas when we derive this version for the real number that is only restricted to rational number, we do not involve at all any exponential function. So you can see, try to see the importance of exponential function. Without it, you would not be able to arrive at the derivative of the generalized power function. So once we have done this, the rest is just to look at a few examples that involve the generalized exponential function. Okay, so the general exponential function has one more slide to go. I forgot how to do this. So we have shown this relationship. Then the next thing to do is to try to generalize this derivative. Okay, up to this point, we have we are talking about the derivative of a generalized exponential function. So when you generalize this, what do you generalize? You just generalize the x to the u, right? So what happened to an generalized power of u raised to power n, where n is the same n as here, n real number, but instead of the single variable u, we have a function of x expressed as u. So this again could then be obtained as using the chain rule, du dx times du times d du of u power n. So this is a chain rule. Then this is just equals to du dx. d du of u power n is just n times u power n minus 1. Therefore, we come to the conclusion that if you have a function u raised to a real number, then the result is obtained as the product of du dx, the derivative of the function u with respect to x, times u raised to power of n minus 1 and multiplied with n constant of n. Here, n could be any real number, including irrational number. Okay, so now I think we are really into the last bit of the slide, which is just example of differentiation of the generalized power function. And in part B is the differentiation of an generalized power function as well, but with x replaced by and function of u. So let's look at the example A here. Okay, so the example A here is ddx of x raised to the power of square root of 2. So this is the example, x power square of 2. So remember here, we are doing the differentiation of x power n, where n is an irrational number. So here the n is just the square root of 2. And the answer is very simple. It's equal to n x n minus 1. So here you just replace n by square root of 2, x raised to the square root of 2 minus 1. As simple as that. That is the result for the first example. The second example is the derivative of an function raised to an irrational number, which is pi. Okay, so where the function is 2 plus sine 3x. So this is essentially like differentiating an function of u raised to the power of n. And using the formula that we have just derived, it is just du dx times n times u n minus 1. So let us work out this function one by one. Here u is 2 plus sine 3x. Therefore, du dx is simply equals to 3 times cos 3x. Okay, so this will be 3 times cos 3x times n. Here n is just the number of pi. Then n minus 1 is just pi minus 1. So I write down the expression of u, which is 2 plus sine 3x raised to the power of pi minus 1. So that is the answer to the differentiation. So up to this point, we have demonstrated how to perform the differentiation of an function raised to an irrational number. We have also shown you how to calculate the derivative of a generalized power function, where the power in the power function or the index in the power function is an irrational number. So that ends up this topic. So let me give you a brief discussion of the summary. In this chapter 7.3, we have discussed the exponential function, which is defined as the inverse of the logarithmic function. So if you know the properties of the logarithmic function, you could be able to tell everything about the exponential function because they are closely related. Then we discuss some rules of the exponential function, namely e power x1 raised to the power of x2 is equals to e power x2 raised to the power of x1 is equals to e power x1 multiplied with x2. Then we also learn that e power x1 plus x2 is just equals to e power x1 multiplied with e power x2. And then we learn that e power x1, e power x1 over x2 is e power x1 minus e power x2. So that was also mentioned. Then there's one more, that is e power minus x is equals to 1 over e power x. Okay, so these are the few properties of the exponential function. Then after that, we have also shown you the exponential function obeying this very simple rule: e power ln x and ln of e power x is equals to x. So this is very easily understood in the sense that the exponential function and the logarithmic function is the inverse of each other. Then we also discuss the differentiation of the exponential function and the generalization of it, which is d dx of e power u. Then we also derive the generalized the integration of e power u, which is equals to e power u plus a constant. And then based on this one, we also make use of e power x to generalize the exponential function, where the index in the exponential function is now included for a real number. And also by using the exponential function, we also generalize the power function to include the index that could now become irrational as well. And then we also discuss the differentiation of the generalized power function, and also the differentiation of the generalization of the generalized power function, which is ddx of u raised to an irrational number. So that is what we have done so far in this chapter. So thank you for your attention.